All right, welcome everyone. Let's welcome Haoran Zhang, a PhD student at MIT, advised by Marcy at the SEMI. He's done some incredible work in robustness of deep learning models and medical imaging. I guess, yeah, some of it with me. I know Haoran since he was a master's student at University of Toronto, so it's been amazing to watch him grow into like a faculty candidate at some point. Also makes me feel old, but welcome.
Thank you.
And go ahead.
Great. Thank you for the introduction, Shamli. So I'll be talking about some of my work on characterizing and repairing failures of machine learning in the wild. So as we all know, machine learning models are currently being deployed in clinical settings. And so as an example, if you walk into the ER today with symptoms of chest pain and cough, you might have a chest X-ray taken like this one. And your X-ray may be passed through a FDA-approved triage model, like Any's triage here, which determines how long to wait before you see a doctor. And subsequently, if you're then admitted to the ICU, your labs and vitals may be also passed through an FDA-approved algorithm like this one to determine your risk for sepsis, and then subsequently determine how doctors will treat you. But we know that clinical machine learning models often fail in new domains. There's been many high-profile cases of their failures. Perhaps the most well-known example is the EPIC sepsis model, which people have heard of, I'm sure. So EPIC, which is a large EHR software company, in 2017 deployed this model to predict sepsis risk in ICU patients. It was trained on 3 US systems from 2013 to 2015, deployed over half of all US healthcare systems. A few years later, after it was deployed, some people from the University of Michigan did a study of this model, and they found that this model basically doesn't work at all. And specifically, it had a reported ARC of 0.676, but the actual ARC was about 0.63, and the TPR, the true positive rate, was around a third. So not a model that you want to deploy in the hospital. And this is by no means an isolated example. There's been examples of models failing. For example, Google's diabetic retinopathy model failed in real-world tests. Real-world ICU models fail under population shift. Even when those work overall well, they may not work equally for all subpopulations. For example, it's been shown that commercially available breast cancer screening models work less well for Black patients and people with denser breasts. And similarly, commercially available risk scores for stroke also work less well for Black patients. And all this is compounded by the fact that datasets often contain errors in the clinical setting. As we all know, oftentimes we use ICD codes to determine disease or other phenotyping methods. And it's been shown that for sepsis, back in the original example, that these codes have a sensitivity as low as 6%. And similarly, even when not only is there bias, not only is there label errors, there's also label bias. And specifically, it's been shown that women are diagnosed with heart disease at much higher rates than men. So my work focuses on the following, which is first, why do clinical models fail unexpectedly? And there's 3 main failure modes in my prior work. The first is label noise. So datasets train clinical ML models often can label errors or label biases, and training on these datasets may lead to subpar models or biased models. Second is fairness, which is that models that, even if they perform well overall, may perform disparately for different subgroups. And here we'll define fairness as differences in some performance metric between groups or differences in calibration between groups. And finally, when we have a fair model that works well in some hospital, deploying that model may lead to failures. This may be due to distribution shifts between some source hospital, some target hospital, or just shifts over time. And then under these failure modes, I asked the question, how can we build more robust models under these failure modes? Now, these failure modes can also co-occur. For example, you might have some intersection of label noise and fairness. We're trying to achieve fairness under biased label noise, or something intersection of fairness and distribution shift. We're trying to achieve fairness under distribution shift, or there are lots of methods that work for both settings. So a variety of prior works in each of these areas. My main application is clinical health, so mostly clinical images, but also sometimes time series and notes. And these motivate problems that are then correspond to machine learning methodology, which then can be applied back to clinical health. So I've published in both clinical journals as well as machine learning conferences such as NeurIPS. But for purposes of this talk, I'll be focused on 2 particular streams of work. The first line of work looks at essentially, do performance and fairness transfer when we deploy a model in a new hospital? And if so, why? And if not, then why not? And then can we explain why certain metrics transfer and why some metrics don't transfer? In the second line of work, I'll be talking a bit about the problem of trying to achieve fairness under biased label noise, and what are the tractable assumptions you have to make to achieve such definitions. Let's start with the first stream of work. Okay, so one illustrative example that I'll be using throughout this talk is the example of X-ray screening. So this is a somewhat contrived problem, but we're given a particular studies from a particular X-ray or X-rays from a particular study. So here, one or more images. Let's assume one image for the sake of this example. And the goal is to predict some set of diseases here, cardiomegaly, pneumothorax, and so on and so forth for this X-ray. And this is a multi-label problem. So images may have one more possible diseases. And this is interesting because 3/4 of FDA-approved models are in radiology. As we saw at the start of this talk, these models are being used in real world. So back in 2021, we had this paper where we looked at one specific prediction task, which is no finding prediction. So no finding equals 1 means you're healthy. Okay, and so maybe you care particularly about the false positive rate of no finding. So this would correspond to me predict someone to have no disease when they have a disease. We call this underdiagnosis. So this may lead to delays in treatment, so we care about this specifically. And when we train a state-of-the-art prediction model to predict no finding, and we plot the FPR, the false positive rate across groups, what we find is that we find significant disparities in FPR rate and diagnosis rate across gender, so worse for females, worse for younger patients, and worse for Black and Hispanic patients. So perhaps the first instinct that you see when you see the result is, what if we just apply fairness methods? There's a wide range of various fairness methods in the literature that can get rid of these issues. So what if we apply them blindly? And then what happens if we were to deploy these quote-unquote fair models in a different hospital? So in this paper published in Nature Medicine, we do this experiment where we train models that mimic CXRs, which from a hospital in Boston, on X-rays. And then we deploy, or we pretend to deploy these models in a bag of hospitals from around the world. So hospitals in Vietnam, Spain, and across the US. So we'll call the Boston hospital mimic CXR in distribution, and we'll call the rest of the hospitals OOD, on distribution. And we'll evaluate both the performance, here we'll evaluate overall AROC, as well as the fairness, here defined as TPR and FPR gaps across demographic subgroups. Okay, so let's start with the first question, which is what happens to these models if we just apply fairness methods on in distribution data, so on Boston data. So on the x-axis, I've plotted the overall performance, the overall AROC. On the y-axis, the fairness gap, the TPR and FPR gaps. Here for cardiomegaly and age as the attribute. What I've shown here are the ERA models, so the naively trained models. And we find that in general, these models are performant, but unfair, or they can be fair, but they essentially have random performance. Here, each shot is the model, and we vary the hyperparameters and the random Cs. So what happens if we apply fairness methods? Can we get a better trade-off between performance and fairness? And the answer is yes. So we apply some state-of-the-art fairness methods, which either balance the groups, or they apply some loss weighting. And then we find that indeed, there are many various methods that give us a better empirical Pareto front, so the best trade-off between fairness and performance. And in particular, there are all of these models which seem to have just as good performance as ERM, but are much fairer than ERM. So this might be a good result, right? That essentially we can de-bias data, de-bias models in Boston. But let's go to a new hospital. Let's now go to Stanford and Vietnam and Spain. What happens if we were to deploy these models in those hospitals? So here we're going to make plots that look like this. So this is for a particular combination of task and attribute. We can plot the in distribution, so the Boston AROC, and then the Vietnam and Spain AROC. And we find that the correlation is very high for this particular combination of task and age, the task and attribute. So what this means, if you want a performant model, a good performing model in Spain, you should choose a performing model in Boston. We can do the same thing for fairness. So here in distribution TPR gap and OOD TPR gap. And again, we find the same result, which is if you want a fair model in Spain, you should choose a fair model in Boston. But let's do this for the other combinations of task and attribute that we see here. So we can plot this these plots as a combination of the R values. So here R equals 1.0, R equals 0.98 in the super plot. And again, this is the top right corner because both correlations are high. Let's do this for the other combinations of task and attribute we studied in our paper. And we find the following, which is that across all these combinations, performance transfers well. So the performance correlation is always above 0.95. So all the performance plots look like this or this, which means, again, if you want to have a performance model in Spain, choose a performance model in Boston. But fairness does not transfer. And specifically, there are many cases like these ones here or these ones here, where the correlation is very low or even negative. So for these hospitals, what you actually are saying is that if you want a fair model in Spain, you actually want to choose an inferior model in Boston, which doesn't make a lot of sense. Okay, so then this leads to the question of why does the performance transfer across domains, but why does the fairness not transfer? Or in general, why do some metrics transfer and why do some metrics don't? And when some metrics don't transfer, what can you explain why they don't transfer? So that's the next part I'll be talking about. which I did with Shamali back in HTML 2023. So the setup is the following. We have some source domain. So this could be a particular hospital, could be a particular subgroup with some known accuracy, say 76%, and some target domain, so a new hospital or across time or a new subgroup with some lower accuracy, here 13%. Suppose we're doing a task for mortality prediction. You might ask the question, why did the model fail? So let's formulate the problem a bit more. We have some system variables, V, composed of X and Y. Y is our prediction target. And here we can decompose X into XM. These are the variables that our model takes in as input. And XM complement. These are the variables that our model doesn't take in as input, which may still influence the performance of our model. We have some model that takes in XM, L plus Y. And we have some separable loss. Essentially, a loss that can be decomposed as a expectation across populations. So this might correspond to mean squared error or accuracy, TPR, PR, Bayer score, things like that. We have some source domain, the source hospital, where we sample data from some source distribution to get performance on the source. And we sample data from some target distribution to get performance on the target with loss L plus delta. So we're going to explain why this delta happens by decomposing this delta across some subdistributions across XM, XMC, and Y. Question?
So, I mean, intuitively, it's very sensible to have like XMC.
Yeah.
But the complement of something without a specified sort of superset might not be well structured.
Right.
Like, what is this actually? Do you have some structure that you're assuming here on X overall or something? Or is how the patient smelled to the doctor when they walked in? Like, what?
So ideally, so in practice, this is what we observe. So we take the features that we observe and the things that we pass into the model. SMC is everything else that we don't pass into the model that we do observe. In practice, this could encompass anything in the world, but we'll make some assumptions later about what XMC should be in terms of from a causal perspective. Okay, cool. So the first question is, what is the subdistribution we should consider? What should we attribute this delta to in our D sub V, in our system variables? So suppose we have a very contrived example, just for motivating purposes. We have age, blood pressure, and mortality. And suppose we're going to predict mortality from these two variables. This is very underspecified, but just as a thought experiment. We could attribute to shifts in age, shifts in blood pressure, and shifts in mortality. But this doesn't capture any conditional distributions, right? It doesn't capture shifts in mortality given age. For example, the older people are more likely to die in the source than the target. We could have the classic covariance shift and concept shift. So everything shifts in X and shifts in Y given X. But again, the problem is we are not specific enough because we can't attribute the shifts in age only, for example. We could have all possible combinatorially many distributions, but this becomes very large and it's hard to be tractable in a setting because there are exponentially many such distributions. So all possible conditional and joint distributions. So here we propose a separate or a different setting. We propose a setting where we know a graphical model. So we have some prior knowledge about how independencies within the data are structured. And then we propose that the mechanisms to consider are then the nodes of this graphical model and the parents. So here, given this sensible graphical model, the distributions are age, blood pressure given age, or mortality given age and blood pressure. So why is this a good set of distributions to consider? Well, assuming that all variables in the system are observed, which comes back to your question, then this is interpretable and actionable because these graphical models or these causal graphs can be created from domain knowledge. And so their edges, each distribution may correspond to some actual value of the system, some actual thing in the system that should then go in and change and perturb. And finally, if this is a causal graph, then this attribution will be succinct. Assuming that the shifts, if interest are actually things, shifts in causal mechanisms, then we're going to be able to attribute to the actual root cause of the system if this is a causal graph. Okay, so again, summarizing,
You said when you were first listing the sort of desiderata of the way we can break this down, you know, you might want to talk about a distribution within some joint distribution or something.
Yeah.
So, you know, age and blood pressure, I want to do just one. So when you have this causal graph, you're sort of removing some of those things you could talk about.
Sure.
Like you're not talking about mortality just given age here.
Yeah.
And I just want to make sure I understand correctly that you're arguing this is a good thing or intentional because it's not really sensible to talk about mortality given age if you have a causal graph that assumes age affects mortality also through blood pressure or something like that.
Exactly. Yeah. So I think if this is a causal mechanism, then it makes sense to talk about this mechanism as a whole. So mortality given all of its parents. Yeah. Cool. So summarizing the problem again, we have some system variables, age, blood pressure, mortality as an example. We have some known graphical model, which implies a set of distributions that we'll consider. We have some observed samples from the source and some observed samples from the target with loss L1 plus delta respectively. And as a simple example, if suppose that two of these distributions shift, so age and blood pressure given age shifts, we're going to attribute some delta 1 and delta 2 to these two particular shifts. And as the normalizing factor, we'll set these sum up to the actual shift delta. Okay, so this is the form of the attribution that we'd like to have. The question is, what should we actually assign as delta 1 and delta 2? So here's a motivating example. So coming back to this example of age, blood pressure, mortality, in the source domain, we know that these distributions take their source values. So there's some source distribution of age, some source distribution of blood pressure given age, and so on and so forth. The product of these distributions corresponds to the actual source overall joint distribution. And we know the performance of our model on this distribution because we have samples from this distribution. On the target domain, everything is shifted. So here, everything takes its target values. But again, we know what this distribution is, or at least we observe samples from this distribution. So we have an estimate of the performance of our model on this distribution. Let's suppose that we're trying to attribute the shift across these two performance metrics to age. How should we do it? The key inside this paper is that we consider what happens in the world when age shifts. Suppose we have this world now, where it's a world where age takes target value distribution, and then blood pressure given age and mortality given age and blood pressure take their source distribution values. Right? This is still a joint distribution over the system variables, and it makes sense that this is now a joint distribution of system variables. So there's some performance of our model on this new world where only age has shifted. Now this performance is unknown because we don't observe samples from this distribution. So in the paper, we propose to compute this performance using importance weighting, a classifier-based approach to computing importance weights, which we'll talk more about if there's interest later on. So assuming that we can estimate this quantity, we can then have our first term, which is the performance of our model in the world where only age shifts, and the performance where nothing shifts, the source. So this makes sense as a term because this is essentially the contribution of age to this difference where only in the world where only age has shifted. But we're not done, because it's possible that these mechanisms will shift independently, and so it's possible that blood pressure given age has shifted as well. Right? So what happens if this shifts? So if you're in this world where blood pressure given age has shifted, and then age shifts on top of that. So there's now two more worlds. So it makes sense to think about the contribution of age as a difference in performance between these two more worlds, which is the contribution of age when blood pressure given age has shifted already. And finally, there's a fourth world where these two shift, and then age shifts on top of that, which is essentially the target distribution. So the contribution of age when these two other distributions have shifted already. So this is the form of our attribution. We add in some normalizing factors so that they sum up to the actual delta. But this is the proposed form of our attribution. And generally, for an arbitrary distribution D, we first sum over every other possible combination of distributions that can shift. So here, blood pressure given age, and mortality given blood pressure given age, but possible combinations of those. For each combination, we consider the performance of our model in the world where our distribution D and everything else has shifted, minus the performance where everything else has shifted. And then writing these normalizing factors. So if you're familiar with Shapley values, this is precisely the Shapley value for a game where each player is a distribution, and the total payoff of the players is the performance difference between source and target. So why would you ever want to use this particular form over anything else? Well, it turns out this method has a few nice properties. The first is that the sum of the actual shift will be equal to the sum of the actual attributions will be equal to the total shift, as we saw before, which is what we desire. Second, if something does not shift, so if there's no shift between source and target for a particular mechanism, the distribution will be equal to 0. Third, if for any possible other world that you add your distribution to, there's no performance difference when you shift that particular thing, even if there's actual shift, then the distribution will be equal to 0. So this might be a case, yeah. Mm-hmm. So we observe samples from source and target. So we assume we have observed sample from the source and target, and we're able to compute these performance metrics for some arbitrary distribution using importance sampling. Yeah. And so the third property that we like to have is assuming that you have for any possible world that you add your distribution to, it does not change the actual performance, then its attribution goes 0. So this corresponds to the case where your model doesn't even use a particular feature, and that feature has no relevance to downstream features. Even if that feature shifts, it doesn't matter. We're going to attribute 0 to that feature. And finally, if you swap source and target, then the attribution will be negated, which makes logical sense. So our attribution is the only attribution that provably satisfies all 4 properties. Okay, so let's do a case study now. Suppose we're doing mortality. Yeah.
So if you were to just look at what happens when you change A.
Yeah.
I understand that this would sort of underestimate or not underestimate, but estimate differently.
Yeah.
The impact that age has because maybe other things have shifted too.
Right.
But is this, you know on your actual source data that those other things are what they are, right? So if you were to ask, like truly, if you were to take your source data and only change age, then it would just be that first term, right?
Mm-hmm.
So is there something here where you're, there's sort of almost like an analogy to like a partial derivative and a total derivative here, where you're looking at like across a wider range of possible changes as opposed to like just in a specific direction? And does that affect the interpretation of these attributions, or am I just totally misunderstanding them?
So that could potentially work, yeah. So this is, logically a perfectly valid attribution to the shift in age, right? But I think the main problem is that you wouldn't be able to get these properties if you had that attribution. Yeah, but that's a totally valid attribution as well in this problem. Cool. So let's consider this case study for mortality prediction in the ICU. So suppose this is EICU data. So we're trying to predict mortality given any numerical features. And suppose we're trying to, we train some model in the Midwestern US on 6,000 examples. We're deploying this model in the Southern US with 250 examples. Suppose during deployment, you monitor performance drop. And specifically, we're here evaluating the Breyer score, which is essentially the mean squared error for prediction, probability prediction. And so you observe a higher Breyer score, which means worse prediction on the South than the Midwest, on the target than the source by around 50%. Okay. So I'm going to ask the question, why did the model fail? Why did the Breyer score increase by 0.037 between source and target? So first, we need a causal model, right? We need a graphical model of the system. Now, if there are no absolutely zero knowledge about the assumptions about the possible structure of the data, then you could go with this graphical model, which is simply x causes y, right? You could stick all of your features into this particular supernode of dx, and then you have mortality given x. Assuming this is a causal system, this is a perfectly valid graphical model that you could run attributions for that will give you shifts in x and shifts in y given x. So even when there is no knowledge about the causal structure, you could still do something with this method. But luckily for this data set, we have a paper, a previous work, that runs causal discovery on this data set. Here they've proposed the following graphical model, for example, with knowledge of age and gender independent, and so on and so forth. Okay, so we can run our method on this data set given this graphical model, given this causal graph. And what we find of that 0.037 Breyer score shift is the following. So there are two distributions that account for the majority of the shift. So the first is shifts in age. So about a third of the shift is shifts in age. And specifically, there are more older people in the South than the Midwest, if you plot the distribution of age. So this might lead to some targeted mitigation strategies. This might, for example, suggest collecting data from Midwest in more older people. And if you do that, you can reduce the performance difference by about a third. As well as improve performance in the target distribution. Okay. And then next, about a third of the shift is due to shifts in lab given gender and age. So what this means is, given a particular gender and age, the labs still look different between the South and the Midwest for the populations. So this might lead to a targeted domain adaptation strategy where we weigh examples in the source, so in the Midwest, based on how similarly their labs look to the South, just for that particular triplet. And again, what we find is that if we apply this method, we're able to reduce the performance difference between source and target, as well as improve performance on our target domain. So what we found is that we can use our method to actionably attribute performance differences to specific mechanisms, and then apply interventions that lead to better performance on the target, as well as lower performance difference between source and target, leading to more robust models. Any questions?
graph from source or the target data? What if the causal discovery that give you different
Yeah.
values from?
That's a good question. So this paper, I believe, learned on everything. Learned on the joint data sets. So in practice, if the graph is off, then our attribution method will be wrong by a bit. So with some empirical results that show, depending on how off it is and depending on what shifts, it may be, the attribution may still be reasonable or may not be reasonable at all. But I think the graph being accurate is very important. Yeah. Mhm.
So, yeah. But at the end of this, I still see the decrease from 0.79 to 0.68.
Yeah.
How far can you get with this methods and modifications?
Yeah, that's a good question. So I think the Oracle baseline, which I'm gonna have here, is if you just trained on the full South data set. If you had a lot of samples on the South, you could just train on that and then get the best possible performance. So I think in the paper, we have the number maybe 0.05. So there's still a ways to go if you only have access to some limited South data. Yeah.
So you mentioned that if the causal graph is wrong, your attribution will be off.
Correct.
But your attribution also theoretically satisfies some properties. Do those properties only hold if your causal graph is correct? In the sense of because you said the performance discrepancy will be broken down, will be a sum of the attributed discrepancies, right? If that is always true, then I guess my question is sort of what does it mean for the graph to be wrong? And how is your attribution wrong in that setting? It still decomposes like that, right? Because you're still saying here are differences that cause an effect.
Yeah, that's a good question. And so all of our proofs and theorems assume this case, right? Which is that the shifts are due to shifts in one or more mechanisms. And so if you have observed things shifting, for example, then you cannot possibly attribute to that. I think you will be able to attribute to the downstream aspects, but that won't be succinct. Yeah, but I think given that we use a Shapley value estimator, these properties should hold no matter what. But again, I think it's a succinctness and the actual root cause attribution that's different.
I see. So it's not really the causal graph that needs to be accurate, but the distribution shifts need to be limited to those implied by the data.
Correct. Yeah.
Okay. And then I guess my other question is, oh no, wait, I forgot it. I'm sorry. I had another one, but now it's gone. Please.
Okay, no problem. Okay, so that's the first one. Yeah. Okay.
So some problems are just harder.
Yeah.
Like in some setting or another, not necessarily like, it may be that it's harder to discriminate. It doesn't seem necessarily the case that you can always get a performance gap down to 0.
Sure.
How does this square with your statement here that you can actually go through and make targeted interventions to sort of mitigate distribution shifts? Because if you mitigate distribution shift to 0 by your theoretical properties, the performance gap will go to 0.
Yeah.
Does that mean that implicitly you're going to be worsening performance on your source data set or something in order to make that?
Yeah, that's a good question. And so there's definitely irreducible error differences between domains, right? It's possible that it's impossible to have a model that has zero difference without making the source one worse. But here the attributions we have are just actual that make link to those irreducible errors, right? Yeah. And it's possible that mitigating these may not lead to 0 attribution eventually to these particular edges, if that makes sense.
Okay. Yeah.
Yeah. Okay, cool. All right, so next I'll be talking about stream of work on looking at fairness under bias label noise. Okay, so the motivation behind this is that healthcare data is often mislabeled more for specific groups. As we saw at the start, for example, physicians misdiagnose women with heart disease more often than men. And specifically, this paper showed that women with heart disease are more often misdiagnosed with mental health issues than men. And similarly, there's many flawed automated processes, such as ICD codes, that we use as labels for a particular prediction task. But coming back to this example at the start of X-ray predictions, where do these labels come from that we use to train our X-ray models? And so it turns out that it comes from the following pipeline. So the radiologist looks at the X-ray and writes some radiology note, right? And then these notes are parsed by an automated NLP-based labeler, which extracts binary labels from these notes. It turns out this labeler is pretty bad. So this labeler has a 50% F1 score for normal finding extraction. And overall, studies have shown that a radiologist looking at the image versus a radiologist looking at the note has an agreement from 0.4. So certainly this process has a lot of noise, both due to the labeler being inadequate, and also the pipeline and the radiologists disagreeing and being noisy. But is there label bias? That is, does the rate of error differ between groups for this particular problem? So we ran pilot, this is ongoing, to collect disease labels from radiologists. So for about 4,000 images, 4,000 studies, we surveyed 3 radiologists. We took the majority vote for 12 disease labels. And we can plot this for each particular demographic group. We can plot, assuming that the radiologist label is correct, is the gold standard, we can plot the accuracy of this pipeline versus that gold standard. What we find is that overall, the accuracy is around 85% of the automated pipeline. Compared to the average physician accuracy, there's still room to go. So the average physician accuracy, that is the average random physician versus the majority vote, has an accuracy of 92%. So there's still noise to be eliminated from this pipeline. But looking at label bias, we find there's no label bias between gender groups. There's no label bias between racial groups, but there is label bias between age groups. Specifically, there's a much worse performance of this automated pipeline to extract the labels for older populations. So the motivation behind our method is then, how can we learn models under this label bias such that we can reasonably at least try to get a correct and fair model for the more label noise population, the older population, given only noisy examples. Okay, so some formulation here. We have some true labels which are never, yeah.
Are you considering the concept of using your prior method to ask where does that performance between these groups come from in the actual physician and then automated extraction work?
That's a really good question, and so we've not tried that. That would be a good next step. So we need a causal graph though of the system, y causes y hat, and something like that. Yeah. But that's a good suggestion. So we have some true observed labels that we never observe of k possible classes. We have some noisy labels which we do observe k classes, so we're doing multi-class classification. And then with some groups which are known. Suppose we have this very simple example where we have some underlying ground truth again. There's men and women. We're trying to predict healthy or sick. Okay, and due to some flaws in the pipeline, we instead have some label flips. For example, this healthy man was flipped to a sick man. The first thing we need though is to think about what is the structure of the noise. That is, what assumptions do we make about the noise structure, about how noise is added to these populations so the problem is tractable. Because if you allow any random noise to be added to the system, then it becomes not tractable theoretically. So we make the following assumption, which is to assume that conditioned on a particular label, which is unknown, in the group, the observed label is independent of everything else. So this corresponds to is basically for a particular combination of Y and G. So for men with pneumonia or for women who are sick, the chance of a label flip is uniform within that group. There's no more separation within that group. Okay, so this is certainly a very strong assumption, and it's unrealistic in many cases, but this allows us to have tractable theorems and methods in a setting. So in this assumption, we can parameterize the noise by a matrix for each group. And here, each matrix actually corresponds to essentially the probability that we observe a noisy label given a particular true label in the group. So 0.5 is the probability that we flip a sick person to a healthy person given that you're a woman. So this person here was the victim of that label flip. Okay. And then we define label bias as when these matrices differ. So when the structure of the noise is different between men and women, we're going to call that label bias for this problem. Okay, so it's one concept. The second concept is fairness. So here we're dealing with models that output some risk score distribution. So here outputs a score distribution over your possible k classes. And previously we saw one definition of fairness, which is equal TPR and FPR, so equal underdiagnosis rate between groups. And this is called equal odds. This is a perfectly fine definition of fairness, but for score-based models, you have to do some thresholding or some approximation. So I think a more natural definition for score-based models is this one called group sufficiency, which says, this is the following appendix statement, but essentially says that we want equal calibration between groups. So what that means, if you plot a calibration curve for women and the calibration curve for men, we want these two curves coincide. Okay, so saying that we want the same calibration curve for the both groups, that's a risk score means the same thing for both groups. That means if I predict a risk of 30% for men and 30% for women, that they correspond to the same meaning for both groups. So in a case such as this one, where they don't coincide, where there is a gap in calibration, how do we measure that gap? How do we quantify that gap? So we propose a method called the sufficiency gap. So this is where we take a particular group's calibration curve, so the calibration curve for women here. We take the marginal calibration curve, which is the curve for everyone in your population, regardless of gender. And then we take the error end of the curve, the weighted error end of the curve, between the females curve and the marginal curve. So we're going to call the sufficiency gap for females. Here's a mathematical expression for the Monte case. It's not too relevant. And then we can average across the sufficiency gaps by group to get our overall sufficiency gap for the model. Okay, so this is the quantity that we'll try to minimize for a problem, assuming that we have equal good utility as well. So we want to minimize the sufficiency gap of our model subject to good utility for our model. Okay, so the main contribution of our work is some theory looking at when does label bias, that is, when the noise structure difference between groups, imply group net sufficiency and vice versa. So the most compelling theorem I'll show here, which is under label bias, so under the fact that there is biased label noise in your dataset, and under the fact that you have group sufficiency on the noisy labels. So this may happen if you naively enforce fairness on the noisy labels. And then the amount condition on the scores, which basically responds to, in the binary case, your scores not being the same for everyone. Then you will necessarily have a non-zero sufficiency gap on the true labels. So what this means is if you naively enforce fairness on the observed labels, if you don't know about the label noise, you don't care about the label noise, then you will necessarily have an inferior model when you actually go to deploy the model. Okay, so this motivates having methods which are label noise aware. There's methods which have knowledge of the transition matrices or knowledge of the noise within the data, and then achieving fair models on the true labels given that particular structure. So that's what we propose in our method. And so first, we have our theorem will be upper bound to the sufficiency gap for this quantity, which is the conditional information between y and g given our score f of x. Okay, so if this is 0, then we have sufficiency. So we can add this term in our training to our loss weighted by some lambda, as well as some prediction loss, which may be cross entropy or some noise aware loss. So this is pretty simple. We just minimize this, right? But not quite, because we don't observe the actual transition matrices. So first we can estimate the transition matrices from data. So that's the first step. But the second thing is, even if we observe the transition matrices, we don't observe the true y. And so we can adjust for this factor. We can come up with an unbiased estimator for this CMI, given only noisy labels and given our estimated TGs. Yeah.
The noise transition.
Yeah, so we use a prior work for that. We'll get to that in a second. Okay, so first, let's assume we know the true T's, and assume we have synthetic noise that matches our assumptions. So under these sort of perfect cases, the most synthetic case there is, on these fairness datasets, we do pretty well. So we can achieve lower sufficiency, and for any combination of the noise that we add, or any combination of the loss that we add our regularizer to, as well as higher overall performance. We beat the baselines, but we don't do as well as the Oracle, which is trained on the true labels. So there's still more work to be done. But this generally holds across different datasets. And if you use a prior work to estimate TG, which essentially corresponds to training a model, an error model, and then doing something with the confusion matrix to compute the transition matrix, then it does slightly worse as well. Okay, but let's go back to our real setting, to our setting about X-ray noise and learning under this setting. So we had our pilot study, our data set of 4,000 real labels for our X-rays. Let's use that as a test set. Okay, now the noise between this pipeline and the true labels is certainly more than just classical conditional. So this doesn't satisfy our assumptions, certainly, because there are, men with pneumonia who have harder and easier cases within that group. But let's apply our method anyways and might just work without the assumption holding. And so the question we're trying to answer is, are ER models actually predicting disease, or are they actually predicting the output of this flawed pipeline? So first, let's look at performance across age for state-of-the-art models trained on X-ray prediction on Mimic CXR. And first, let's look at the noisy test. So this is a data set that's released with every single X-ray data set. This is what everyone tests their models on currently, is noisy. So here we can plot the AROC, the sufficiency gap, and the false positive rate of our models. ERM is the naive baseline, and then these are two noise-aware baselines. This is our method. Okay, so we find the noisy test, as expected, we have this under-negligence gap. And we find that generally ERM is well calibrated on the noisy data, which if you remember the theorem is actually a bad sign. Let's move on to our collected data set, our gold standard label data set. We find the following, which is that first, overall, all models have much worse performance for the young and the old populations, for the 18 to 40, 80 plus populations. And none of the methods really improve on performance in that setting. So none of the baselines, none of our method does not work in this new setting. We find that all methods don't satisfy the sufficiency definition of fairness, including ours. And we find that nothing works for FPR either. Okay, so takeaway here is that on realistic noise, existing methods, including ours, don't improve over ERM, don't improve just training a model on the noisy data set. So I think this motivates new methods that work for these more challenging types of noise that we encounter in real-world health settings. Okay, any questions so far? All right, so to summarize what I've talked about in my prior work, we saw that clinical ML models often experience degradations in fairness, for example, in new domains, and they will contribute performance or fairness drops to specific distributions between source and target. We saw that clinical ML data, such as X-ray DSS, contain label bias, and that theoretically training label bias data leads to biased models. And we saw that existing methods empirically don't improve over ERM in these real-world settings. Okay, so what's my future work? What do I want to work on in the future? Well, my work looks at holistically characterizing and improving the reliability and robustness of clinical machine learning models across all of these possible areas. So what models are people currently deploying right now? Well, the answer is clinical language models and vision language models. And so back in 2020, we had this paper with Matthew McDermott looking at benchmarking, one of the first benchmarks of fairness in clinical language models. Now, this was a small language model. This is Cybert. And so we had this flashy example on the first page of the paper where we had this prompt, race patient become belligerent violent, sent to blink. And Cybert completes this particular sentence, sending some patients to the hospital and some others to prison. Okay. And back in 2020, when we submitted this paper to a fairness conference, one of the reviewers said, this is completely unrealistic because no one will ever apply, language models to clinical text. Why would they ever want to do that for predictive modeling? Well, fast forward to 2006, and now this is happening all over the place. So Bridge, which is a multi-billion-dollar startup, is deploying over 100 health systems. Their ambient scribe company, they listen to you when you're talking to your doctor, and then they summarize the visit into a note. Similarly, ChatEHR at Stanford, which was recently deployed, allows clinicians to chat with state-of-the-art commercial language models like ChatGPT and Claude and Gemini, passing real-world EHR data to those language models. But we know that these models also fail in the wild. So back in 2023, some researchers did a study of these models, and they found that state-of-the-art models at the time propagated race-based medicine. And specifically, they had all these erroneous out-of-date medical facts, for example, thinking that Black people have thicker skin than white people, or that Black people have less nerve endings than white people, which are incorrect. Okay. And on the vision language model side, Google's recent Gemini paper, which was released in arXiv, had an error. And in one of the interpretations of a CT scan, they made up a completely new body part. Okay, so certainly these models are perhaps not as reliable as people think they are in clinical settings. So my research aims to characterize and improve the reliability of these models, both small models like what we saw before, linear models, risk scores, vision models, now including language models and vision language models. So here I use the word holistically. So what does this word holistically mean? Well, I'm thinking of it as the following. So a lot of people evaluate machine learning model as simply something that takes in data and outputs some prediction, right? They evaluate performance of fairness as some statistical property of some predictions versus the data. But the data doesn't come, from magic. It's collected from some process, and the process can have errors or biases. So in this work, we saw a couple of possible such biases. We saw label bias, which some of the labels that we collect may be incorrect, and we saw different types of distribution shift, where the distributions may shift between source and target. So I aim to work more in this setting of looking at clinical machine learning under noisy data and distribution shift. One particular project that's interesting to me is looking at label bias in human preference data. Let's talk more about that. So the idea is the following. We have some human preference data in language modeling. Suppose we have some query that says, tell me about skin thickness differences between Black and white skin. And there are two possible answers. Black people have thicker skin, or that there are no significant differences. Now, as we saw, the right answer is A2. But if you just use a reward model when you're doing your AHF, or you're using human annotator, they might both erroneously choose A1. And if you have a data set composed of such data points, you might have a biased or misinformed downstream model. So I aim to solve this problem by viewing it as a label noise problem. So first, I think we should start by characterizing the data set. The existing data sets, what's the rate of noise and bias within those data sets? Are there actually misinformation within those human preference data sets? And second, certainly we'll need more general assumptions than we made in my previous paper, right? We'll need more general instance-dependent assumptions. So what assumptions are tractable that we can still have theoretical guarantees while learning tractable methods in those settings? I think one interesting connection is looking at multi-group calibration or subgroup fairness, which looks at enforcing fairness amongst all computationally identifiable subgroups. So here, can we basically add more terms to the independence term to instead of YG, now it's YG, X1, X2, X3, and so on and so forth, using methods from empty calibration. And finally, there are all these other methods that don't have any theoretical guarantees that work well empirically. So either based on embeddings or based on training dynamics, and then can we adapt those methods to do ROHF and do those methods work empirically to debias these models? Okay. And some other interesting projects in this bucket include, for example, group fairness under the most general concept shift, where we have general shifting y given x, or some tractable assumptions we can make to get guarantees in those settings. And finally, in the case where we don't have transfer, that some metric does not transfer between source and target, how can we actionably come up with a toolkit for what happens when things don't transfer? So as we saw before, there was data collection, there was domain adaptation. Can we come up with a list of targeted strategies for each type of shift that then we can apply in the real world? Okay, now on the downstream side. So a lot of people think about prediction as the end all of our machine learning model. But certainly in the clinical setting, these predictions are passed into some downstream decision maker, or some clinician, which will then use their own knowledge to make the final diagnosis and treatment. So you could have a perfectly performant or fair machine learning model, but if the clinician doesn't listen to the model, then everything is useless, right? You might have a biased overall system. So I propose to take both evaluation and mitigation, taking this whole pipeline into account. That is optimizing for the overall end goal metric as opposed to just our machine learning model prediction. So what are some possible projects in this setting? So the first is the following, which is looking at evaluating and optimizing models for overall patient outcome, integrating this black box, this clinical decision making into our pipeline. So here's a particular example. Suppose we have some dermatology model. So some machine learning model that looks at a skin image and that puts some disease risk scores. Okay, suppose we have some dermatologist or some PCP who looks at these particular, who looks at the image, also looks at the model output, and then makes some final treatment. Here prescribes cephalexin, which is an antibiotic. Suppose that this patient actually had Lyme, and so the ground truth here was to prescribe doxycycline, which actually works on Lyme. Cephalexin does not. Okay, so existing approaches will do the following. Existing machine learning deployments, all of them, first maximize the performance of this model, right? That is, we train this model offline to maximize, overall accuracy, URC or something. And then to make sure that this model works well enough with the clinician, we're adding a patch. And that patch is generally explainability methods, here maybe GradCam or something else. I'll also include incident quantification and selective prediction in this setting. I don't feel too strongly about those particular methods. And then this is how people generally deploy models. But what if I propose instead to optimize the full pipeline? That's, can we maximize performance of this whole pipeline? Because it's conceivable that the model that maximizes overall performance of the system is different than the one that maximizes performance on our offline data. That is, there's some quirks of the human reasoning that we should take into account when we're training our models. Okay, and how might you do this? I'll talk more about this at 4 p.m. But essentially, we can have some loss function between the ground truth and some the actual physician output, which is simple. But then we can backpropagate to our particular model. Of course, the main challenge is that human mind is not backpropagable last time I checked. So how can we essentially come with a proxy that is backpropagable that then we can backprop to optimize our particular model to maximize the performance? So perhaps we need a model for the clinician behavior of some sort, or in online setting, we can do a reinforcement learning, assuming we have an online environment where the clinician can give live responses. Certainly, once we have a model that's maximized in this particular pipeline, we want to have a real deployment compared with the model that maximizes offline performance, the naive method. And finally, one interesting aspect is that there are many live clinical environments where things change. For example, doctors may adapt to a particular model and change their behavior. Different clinicians may have different preferences or different ways of reasoning about probability. So how can we then adapt this method to different clinicians as well, to tailor to the specific clinician?
So if you think about the clinical outcomes, there is from doctors, there's a final step where the patient actually follow the regulation from the doctors.
Right.
Which is arguably probably more complex.
Absolutely, yeah.
Than they should make a process from
Yeah, that's a good point. And so I think, ideally we would add that in as well. And I know you have some work looking at optimizing that next step, right, which is optimizing the patient to clinician communication step. So I think that could be part of the pipeline as well. Yeah, that would add more complexity to the problem for sure. Yeah.
At this point, why not just sort of think about, oh, we should just be doing like reinforcement learning or policy estimation over the entire sort of medical system, right? To optimize, like, why not, forget predicting the actual thing, but let's try and sort of just optimize the overall system towards a farther downstream objective, even than this particular director.
So you're saying that we don't show the doctor the prediction anymore, or how would that work?
We do showing the prediction as a kind of act.
Okay.
But instead of optimizing to get the right prediction of what diagnosis is, or even to get the doctor to prescribe the right thing, we try and control our set of actions to optimize for what's going to happen to the patient in the next 5 years.
Yeah.
Go further.
Sure.
Why take the doctor out of this role? Like, why do you doctor here if you can optimize the whole pipeline?
Yeah.
Right?
Well, I mean, I think there are definitely systems or problem tasks where the models perform worse than the doctor, right? But they might perform better in some subset of data. So those are cases where we want our model to intervene in some things, but not intervene in others. And the collaboration ideally is better than both clinician or model on its own. Yeah.
Stuff that the clinician knows in context that is not available in the modeling pipeline. Because that's the latent confounding that's
Right.
affecting. So did you mention how you're going to address that?
So this could be part of our model for clinician behavior, but if we don't observe it, then that's not something we can take into account. Right. So, right. So it could be a model that takes in this image and the predictions, but also taking other stuff that we can observe if we can log those metadata. Yeah.
Right, online.
Yeah, so in the setting where we don't have labeled data, let's say triplets of image, model prediction, and action, we can instead have the case where we train this model using reinforcement learning. We will have our model output live to an actual clinician seeing a doctor. This is the image, this is a prediction, make the prediction. And then we can have that system adjust itself over time as our model learns new things. So instead of having a fixed data set where we backprop through to train our model, we can do this in an online setting. Yeah.
Question. So actually, a couple of slides ago, when you mentioned about decharacterizing the label bias.
Yeah.
I just said earlier talk, but that means you have to go through you're trying to see how the actual branches label makes data sets are wrong, right?
Correct.
So we identify the whole process.
Yeah.
We label them.
Yeah. So in the X-ray study, we had a pilot study where we labeled around 4,000 examples with real radiologists. So we got 3 radiologists to label each particular study. We took the majority vote.
Exactly. So
Yeah.
Is how to make it scalable.
Yeah.
This huge amount of data sets. So
Right.
Is there any solution for scalability? If you think about like even more than this, I mean, this is already a large scale.
Yeah.
I think it does take a lot of human efforts.
Right. A lot of money too.
Yeah.
Yeah.
So
So
the scale up, but it's just like doing more. Basically.
yeah. Well, so I think there's scaling from a data perspective, which is just more human labeling, right? But I think algorithms can help with this a bit, which is if we have data like these clean labels for evaluation for sure, and for model selection perhaps, can we learn algorithmically a better model from that alone without needing to add that to the training set? Certainly, if you can label 100,000 images with humans, you can just train on the true labels, and then you're good, right?
And here you have the assumption that the new label will do not have bias.
Correct. Yeah, which is not entirely correct, but at least it's less biased than the labeler pipeline. Yeah.
Yeah, can I have a question?
Yeah.
Not the part where you have yes, this part. So, okay, let's say you can look at the whole system and My understanding is that you intend to use this to recalibrate the model
Sure.
based on the performance of the
Potentially, yeah.
system. But you are leaving out the human here. Is there something, why not also intervene on the human and make the results of this prediction of the performance, help them recalibrate how they interact
Yeah.
with the models themselves?
So that could work. I think so. So I think, I think overall aim to maximize performance of the pipeline, some of that could be action on the human side, right? Different training methods for the conditions or different explainability methods that we deploy. The main challenge there is that those methods are discrete, right? So we can't, backpropagate or optimize those methods effectively as weights of our neural network. But I think potentially if we could, have another set of possible training regimes or explainability methods, then those could be tested over as well for evaluation purposes.
I think troublesome. I find
Yeah.
This picture where you kind of consider human there to be just, and you are recalibrating the entire system.
Right.
Without necessarily looking at human as agents.
Yeah. Right.
To learn this feedback and understand how to influence the performance of the system.
Yeah, but right now it feels like humans not taking account either at all, right, in these risk score deployments. So maybe it's slightly a step up, but there's room to go for sure. I agree. Okay, so maybe I'll just wrap up the presentation and I'll take more questions. So I think one last project idea here is looking at fairness evaluations of language models. And existing language model evaluations often use ad hoc benchmarks where they flip gender or race and see if the prediction changes. But I think those are not valid from a validity perspective. So can we have language model evaluations using actual collected data sets, such as chat data, from natural human interactions with them, not just static benchmarks? And then I think that leads to a question of what does it mean for a model to be fair, a language model to be fair? And what are the fairness modes of language models, which is something I'm thinking more about. But that's my presentation. Thanks for listening. I'll take any questions.
Really out of time.
Yep.
Maybe we can take one question if person need to leave. Just ask if anybody on Zoom has a question because they can.
Anyone on Zoom have a question? You can mute and talk, I think.
Anybody in person?
Quick question for the multi-chair. Exactly, it's hard to have a static benchmark because multi-chair can go infinite different directions. So how was your plan? I mean, you've touched it only probably a minute, so
Yeah.
can you elaborate a little more?
Yeah, so I think the first thing is think about the different modes that language models can be unfair. So we've seen two modes here already, one of which is that there's misinformation, right? Like medical misinformation, race-based medical misinformation. And so I think we can generally correct these without much performance loss for our model on the other stuff, right? But then we also saw an example of looking at discrepancies across predictions for different racial groups. And I think this, like the clinical bird example is one similar example of that. And so there, I think there could also be trade-offs between performance and fairness. So I think, but there are cases where we want to take the race into account or the gender into account when we're making predictions. And there are also cases where we don't. So I think categorizing first the fairness problems into those categories in actual multi-turn data and having an auditing pipeline. I know there's things like a fact score, for example, that could allow us to look at factuality of statements of language models in this setting, for example. But I think ultimately the downstream thing we'll care about is like the treatment effect of our language model for each group. Right? Does deploying this language model in the clinic actually help the groups equally? And does it help both groups significantly or not? So I think that's the ultimate goal, but it's hard to evaluate compared to just given static data.